Welcome back, dear students. In today's session, we will learn about another type of sorting algorithm. So here are the contents. First, we will look at divide and conquer method. Then we will see merge sort algorithm, heap sort algorithm followed by, then counting sort, followed by radix sort, and lastly bucket sort. Let us first see divide and conquer method. Now, divide and conquer method is a method of algorithm design. In this method, there are three distinct steps. First step is divide. Now, in this step, if the input size is too large to handle with, then we divide this input data into two or more subsets, two or more disjoint subsets, rather I must say. Next step is recur. Here, whatever division we did with the input set, we now try to sort this considering it as a sub-problem associated with the data subset. And lastly, conquer step, where the individual parts that are sorted gets merged into one big solution. Okay, so here in conquer step we try to merge the sorted data so that we can get the complete sorted array. Using the same strategy as that of divide and conquer method is based here another algorithm called as merge sort. Now it works recursively, dividing the array into two equal halves, then sort them and combine them. Just now we saw divide and conquer strategy, so it is having three steps. The same three steps are utilized in merge sort recursively. That means we are dividing the array, given input array, recursively, repeatedly into two equal halves. At every iteration, we divide the given array of elements into two equal halves. Then when we have completely divided it into atomic values, then we sort these values and then combine it. Okay, you'll better understand in this with the help of an example. Here are the algorithm steps. First step is to find the middle index of the array. Here we need to, because we are dividing the input array or input set of elements into equal halves, we first need to find out the middle index of the array. For finding the middle index, we have a formula here given: middle equal to 1 plus last minus first divided by 2. Okay, then second step, we divide the array from the middle. Now in the first step we found the middle index, then we did in the second step we'll be performing the division from this middle index. Okay, we try to divide the array into two equal halves from middle index. Now in step number 3, we call merge sort for the first half of the array that we have just divided. Okay, using here merge sort method, passing with the parameter array first, that is the first half of the array, and the middle index. Then in step number 4, we call for the merge sort for the second half of the array, and we continue to do this. In the last step, we merge the two sorted halves. We merge the two sorted halves into single sorted array. Let us see this with the help of an example. You'll better understand this. Now consider this is a given series of elements to be sorted using merge sort. Okay, we know that we need to divide this Now just count the number of elements here. In this case we are having 8 elements. Now we have found the middle index of this array and we separated out them. So we divided this into two equal parts, each consisting of 4 elements. Okay, then we further continue to do this division, right? So if we further split this half into two parts, then these are the two parts that we will be getting here. Similar is the case with the another half, okay, second half. So we first divided it, so this resulted into these two parts. Further, if we divide them, then we'll be getting these atomic values, right? So this 14 and 33, if we divide it exactly half, then they will be separated out as individual elements here. Now looking at this, we then combine the two elements at a time, combine them into one, sorting them, right? So for this purpose, when we combine these two elements together, then these will be in a sorted manner, in a proper order. And we continue to do this. Look at this. So here we first combine it as 14 is less than 33. The order will not change. But if you consider the next sequence here, 27 was greater than 10. Hence swapping will take place between these two elements, right? So we did the swapping here, right? Then for this also swapping was done, and for this also. Now when we combine this part into this, we again need to perform sorting. Hence this resulted in this particular half, and this has resulted into this particular half here. Further, if we try to merge these two halves, then we again need to carry out sorting, and hence the sorted elements are as shown here. Now the time complexity for merge sort, in the worst case it is n log n. In average case it is n log n, and in best case also it is n log n. Okay, the space complexity is that of n, where n is the number of elements we are having. The method here is merging mechanism, and this is considered as the most stable algorithm here. The next sorting algorithm is heap sort. We have learned about how to build a heap tree, right? Now heap sort algorithm is a popular and efficient sorting algorithm. The concept of heap sort is to eliminate the elements one by one from the heap part of the list and then insert them into the sorted part of the list. Now heap sort is also considered as in-place sorting algorithm. In heap sort, we process the elements by creating either min heap or max heap, and we know the properties of min heap and max heap. In min heap, we know the root of the tree will be having the lowest value, whereas the right child and left child will be having value greater than the parent node, right? Whereas in case of max heap, we know that the parent node will be having highest value as compared to the child nodes. So in heap sort, we are creating elements, we are putting the elements by creating either min heap or max heap. Whether it is min heap or max heap, they represent the ordering of array in which the root element represents minimum or maximum of the array element. Now heap sort basically recursively performs two main operations. In heap sort, there are two operations that are performed recursively, repeatedly. First is building a heap H using the element of array. Second is repeatedly deleting the root element of the heap formed in the first phase. Let us have a look at its algorithm. See, here we have the method for heap sort. It is taking input as an array. Then we are calling for a function called as build max heap to create a max And in this function, we are taking a looping variable I equal to the length of the array to 2. With a step of 2 we are doing this, and we are swapping the elements by checking their values. Okay, so we are checking heap size array. If it is equal to heap size array, that to 1, then we are just calling max heapify. If we know what is the mechanism of heapifying, we just swap the elements by comparing their values. Okay, so if this particular algorithm is calling for a max heap creation, then it will swap the value of parent and child node based on which one is greater than. Now this is the algorithm for build max heap. As I told you that we are calling for max heapify again if the values are not satisfied. If it is not satisfying the property of max heap, then we are calling max heapify function. And here is max heapify function. Here we know that L, we are declaring it as left of I, that is I is the parent node, L is the left child of the parent, R is the right child of the parent. If L here is, if we are taking the value of L, if it is having the heap size of array and it is greater than that of if it is greater than the parent, then L is the largest value and we are swapping it, right? L's largest is equals to I, whichever is greater from this, then we are assigning it to the largest, hence we are swapping the values over here. I hope you are able to follow me. Let us have a look at an example. Let us consider this is the given series of elements 81, 89, 9, 11, 14, 76, 54 and 22. Now here first we have to construct a heap from the given array, and then we will convert it into max heap. So if we are just taking this as the input array and we are just trying to put them in the form of heap, rather in the form of tree, so it will have a structure like this. This 81 will be the root node, then 9, then we will come to the left child, that is 89, 9 goes to the right child, then further we expand their branches, and this is how the tree will be created. Okay, now in order to convert it into max heap, what we need to do, we need to find out the largest element from this, and we have to replace this largest element with the root element. So here it takes the swapping. See, 81 goes down, 89 comes up, 89 becomes the root here, then 81 goes to the left child, 76, see, look, from this also we need to heapify here. So 76 goes up, 9 comes down, right? And again here 22 goes up, 11 comes down. So this max heap is generated after calling max heapify function. Now after converting the given heap into max heap, the array elements will have this form. This will be the series of the array elements. Now the series is changed. Now next we need to delete the root element from the max heap. We'll remove the root element from the max heap. To delete this node, we have to swap it with the last node. This is what we have seen in remove heap, right, function last time when we were dealing with the heap. So here if you want to remove the root element, so simply you need to replace the value of the root node with that of the last node, and in this case the last node is 11. So after deleting 89 from this structure, right, it has taken place. So this will be the structure of the heap now after deleting 89, which was the root element here. Now after deleting the root element, we again have to heapify and convert it into max heap. Again we need to check whether it satisfies the property of heap. If it doesn't satisfy, then we have to perform heapifying. Okay. So after heapifying, the elements will be swapped again, and this results in this particular structure that is given to the right side. here on the slide. Now after swapping the elements 89 and 11, the given heap will be converted into max heap and the elements of the array will be, now the array elements won't include 89 here, right, because 89 has been removed from the heap. In the next step again we have to delete the root element. Again we need to delete the root element again, and root element is now 81. After deleting it we have to replace it with the last node, and here in this case last node is 54, so it will be replaced here. The structure, resulting structure is shown here to the left side. Now again checking this, it doesn't satisfy the property of heap, max heap, so we need to carry out heapifying module here. Okay, so the resultant structure is as shown to the right side here. Next, after swapping out 81, the array elements will be like this. Now it won't include 81, so 76, 22, 54, 11, 14 and so on. Now see, we have removed these two elements, right? In the next step we need to again remove the 76, that is the root element. So this root element will be removed from the heap again. Then again we perform heapifying. So removing 76 will result in this structure. 9 will be at the root node, and to satisfy max heap property we will be heapifying the structure again. Okay, and this is the max heap that has resulted after heapify. Now here is the array elements after removing 76 from the series. Okay, now next we need to remove 54, right, as this was the root of the tree. After removing 54 from the root and replacing it with the last node, that is 14, this is the tree structure here, or rather heap structure. Then again, because the properties are getting violated, we need to heapify it. Later on we need to remove again the root node, that is 22, and see what heap structure we are getting here. Now we have only few elements left in the heap. So this is 11, 14 and 9. After heapifying, 14 will go up, 11 will come down, and this is the structure, right? And this is the array series that is forming here. Look at this. Now in the next step again we need to delete 14. So ultimately there will be only 2 nodes left. Since 9 is smaller than 11, swapping will take place and this will result in the structure. Now here again we need to remove the root element and it will be replaced by the last node. Okay, so resulting finally left over with one node, and finally that node will also be removed. So now this heap will be lastly empty, and this is the sorted elements that we are getting after complete removal of each and every node from the heap. And here is heap sort algorithm. I hope you have followed this. Now the time complexity for heap sort in worst case as well as in average case and best case is n log n. Okay, whereas the space complexity is O1, and this is also called as in-place sorting algorithm, whereas it is not considered as the most stable sorting algorithm. Let us move on to the next sorting techniques. Sorting in linear time. Now here we are having 3 types of sorting techniques. First one is counting sort. Now this sorting technique is based on the keys between specific ranges. Now this particular sorting and the following sorting technique are somewhat different from those that we have learnt earlier. Okay, now into this counting sort, this is basically based on the range, specific ranges. And sorting is not performed by comparing the elements. There will be no direct comparison between elements, right? Rather, this is done by counting objects having distinct values, like hashing. Like in that case of hashing technique, we will be counting here the number of distinct objects and then perform some arithmetic operation to calculate each object's index position in the output sequence. This is not used as a general purpose sorting algorithm. It is effective when range is not greater than the number of objects to be sorted. Keep in mind, this algorithm will be effective only when the range of the numbers that will not be greater than the number of elements you need to sort. It can be used to sort the negative input values too. Here goes the algorithm here. Counting sort takes the input array and it counts the, here n is the size of the array. Okay. Now we have another quantity called as max, which will find the maximum element in the given array or in the given series of elements that needs to be sorted. Then create a count array with size maximum plus 1. Now here we will be creating a count array with size. Here only we have calculated the max value, right? So we are creating a count array with size 1 greater than the maximum value. Then initialize the count array with all zeros. Now that we have created an array of this much size, max plus 1, now initialize them as all zeros. Now here we will be taking a looping variable I, which goes from 0 to n, and in this loop we'll try to find the count of every unique element and store that count in the ith position in the count array. See here, in this case, in every iteration we will be counting unique elements in the given series of elements and then store that count in the ith position in the count array. Okay, whatever will be the value of I, at that position will be keeping this count value in the count array. Then for next loop, where j is equals to 1 to the maximum size of the array, we now find the cumulative sum and store it in the count array. Then again we take some looping variable here from in reverse order, from maximum value to the lowest value. We restore the array elements and decrease the count for every iteration or every restored element. Let us understand this with the help of an example. Let the given series of elements of the array be this 2974184. Now here, using counting sort, we will find the maximum element from the given element, right? So find the maximum element from the given array. Let max be the maximum element. So here in this series, the maximum element is 9. Let us assign it to max. Okay, so here we have assigned it to max variable. Now the remaining elements are as shown here. Now, in the next step, we initialize the array of length max plus 1. What is max? Max is currently having value 9. So we will initialize a count array, right, with max plus 1, with having all 0 elements to it. So this is our counting array here, which we have created using max plus 1. So it is having value 0 to 9, that is total 10 elements, and which are initialized to all 0. Now we have to sort the count of each array element at their corresponding index in the count array. So for doing this, the count of an element will be stored as suppose the array element 4 is appeared 2 times. See, in the given array, if suppose one particular value appears 2 times, so what we will be doing in the counting array, will be storing the number of count of that particular number at this position. So if suppose 4 appears twice, we'll be counting it as 2 and putting the value in count array as 2 here after this index place. Okay, 4. So 4 appears twice here, 1 appears once, right? 0 doesn't appear here, so it is 0. Then 2 is appearing once, so we have written here 1. Then for 7, 5 is not there in the given array, 6 is also not there, hence we have replaced it with 0. Then 7 appears once, 1 time 7 is appearing, so we have written here 1. Then there is 1 time 8 is there, so hence we wrote it 1, and 9 is also present 1 time, right? Now store the cumulative sum of the count array elements. So here we have stored, and it will help to place the elements at the correct index of the sorted array here. Now see, in the next step what we will be doing, we'll be accumulating it. Okay, we'll be adding them. See, this appears 1, there is so here how many quantities are there? 1 plus 1 is 2, so here what we will be doing, replacing it by 2 here. Okay, then cumulative, that means you have to add it with the following number. Okay, so 1 and 2 is also 1 time, right? So here we will be replacing it, it is 2 again. How we are doing this? Because 1 appeared 1 time, 2 appeared 1 time, isn't it? See, this and this, we have added it together and we wrote it in place of 2. Similarly here, 2 appeared once and 3 is appearing 0 times. So this will be replaced like this. Okay, so here finally we are writing it like this, then it is 2, and here it became 2 because we have added it 2 plus 0. Okay, so we are just adding them together. Okay, cumulative count. Similarly, the cumulative count of the count array is given by this, right? So the cumulative count is given by this: 0, 1, 2, 2, 4, 4, 4, 5, 6 and 7. Now find the index of each element of the original array. Now here we need to find the index of the original array. So for element 9, the index in the count array is this thing. What value we are getting out of count array, right? So we'll be just subtracting 1 from this 7. So ultimately we'll be getting 6. So in output array, 9 will be occupying index number 6. And after placing at each element at its place, now we need to decrease its count by 1. When we have placed an element in the output array, we need to decrease its count by 1. And before placing the element 2, its count was 2, but after placing it at its correct position, the new count for the element is 1. Now for element 2, just see, in the original array, here in the counting array, so here we will be subtracting it by 1, so it will be having index position 2 in the output array. Okay, similarly here we get the sorted output. For doing all of the things with every element, we'll be getting this sorted output array. Now the time complexity for counting sort is, in best case, it is O n plus k. and in average case too it is the same, in worst case also it is the same, and the space complexity is O max, the max variable that we are taking here, and it is considered as the stable algorithm. Now the next sort is radix sort. Now this sorting mechanism is somewhat different from the other one. It is based on the least significant digit to the most significant digit. So here the sorting will take place in this fashion, from least significant digit to most significant digit. This algorithm requires the number of passes that is equal to the number of digits present in the largest number among the list of the numbers. See, whatever the array elements are given to you, among all of these elements, you need to find out the largest number and then find out its number of digits present in the largest number. So this algorithm requires those many passes. If the largest number is of 3-digit number, then radix sort algorithm requires 3 passes to create a sorted list of array. Now here goes the algorithm. In step number 1, we define 10 queues, each representing a bucket for each digit from 0 to 9. See, try to understand this. In the first step, we are defining 10 different queues, and these queues represent a bucket for each digit from 0 to 9. 0 to 9, 10 digits are there. Hence, we are creating 10 queues here. In step number 2, we consider the last significant digit of each number in the list which is to be sorted. In second step, we will consider the least significant digit, the last digit of each number, and we will sort the list according to this least significant digit. In step number 2, each number into their respective queue based on the least significant digit. We will try to insert these numbers into their respective queues based on their last digit. Okay. In step number 4, we try to group all the numbers from Q0 to Q9 in the order they have inserted into their respective queues. In step number 5, we repeat from step 3 based to the next least significant digit. In step number 6, we again repeat the same procedure from step 2 until all the numbers are grouped based on the most significant digit. So this is similar, that we are beginning with the unit place, tens place, 100 place, 1000 place, right? We need to first find out the digits, number of digits in the largest number in the given series of elements. Okay, and then we one by one we switch to every digit, that is every place, either beginning with the unit place, then tens place, then 1000 place, and so on, coming towards the most significant digit. Let us understand this with the help of an example. Suppose the given series of elements of unsorted integers is given here. There is 82, 90, 100, 12, 150, 77, 55 and 23. In step number 1, we define 10 different queues as shown here. So Q0 is there, Q1, Q2 till Q9, 10 different queues we are having. Now beginning with, here we need to find the largest number in the given series. So largest number is 901. Then we need to find out how many digits are present in this 901. So we found that 3 digits are there. Okay. So now this algorithm will take 3 passes to form a sorted sequence of elements. Now step number 2, insert all the elements, all the numbers of the list into respective queues based on least significant digit here. So we are starting with the last digit, right? So using this last digit for every number here, we try to put them into different queues. So if this is 23, then it will be put into queue number 3. Place this 23 value into Q3. Then 55 is there, so we are placing this into Q5. Then comes 77. We are placing this value into Q7. Then 150 is there, since the last digit is 0, it goes to Q0. Okay. Then comes 12. Then now here this is 2 is the last digit, is hence this 12 goes to Q2. Then here we are having 100. Okay, so this 100 goes to Q0 again. This 901 goes to Q1, and 82 also goes to Q2. So here we are starting with in this direction. Okay, from left to right we are proceeding using the least significant digit, and we are placing them into appropriate queues. Now group all the numbers from Q0 to Q9 in order they have been inserted in the order. We have to process in the same order they have been inserted. Okay. Now in step number 3, we are going to insert all the elements of the list into their respective queues based on the next least significant. Now in this case, next least significant is this. Now see here, the sequence of series have been changed. Okay, so the sequence of series have been changed here. Now we are taking out one element from these queues. Earlier we were having this queue, right? So beginning with the Q0, we try to get all the values stored in Q0, then all the values stored in Q1, and hence this series have been formed here: 100, 150, 901, 82, and so on. Now in this step 3, we focus on the next least significant digit. That, as we are having 3-digit number is the largest number, so the middle digit we will be considering, and we try to put these numbers according to these digits. So 100 goes to again Q0, 150 goes to Q5, 901 goes to Q0 again, 82 goes to Q8, 12 goes to Q1, because we are looking at the next least significant digit, the next digit here. Okay, then 23 goes to Q2, 55 goes to Q5, and 77 goes to Q7. Now in the next step we will be coming back to, now this will be the sequence of elements when we take out. Now in the last step we will be considering this particular digit, and we'll be sorting the elements in this fashion. Okay, so step number 4, insert all the numbers to the list into respective queues based on the next least significant. So this is the digit here, and we try to put them to the respective queues. Hence we get this sorted list of elements using radix sort. I hope you have understood this. Now the time complexity for radix sort is ODND. Now D is the number of digits, N is the number of elements to be sorted, and B is the base. That is, we are taking the number of queues or the number of buckets we are taking here. Okay, that is B, and it is mostly 10. In the worst case it will be ONB. The space complexity is ON plus B. Now let us quickly see bucket sort. Now this algorithm is an advanced sorting technique in contrast to all other algorithms. It is considered as a collective framework built using a variety of sorting algorithms. For example, we can sort one of the type of algorithms to sort elements into buckets and another to sort elements within the bucket. See, we can use one type of algorithm to sort the elements into buckets, to place the elements into buckets, and then for in each individual bucket we can adopt another sorting algorithm. We can even recursively implement the algorithm we initially chose to sort each bucket to minimize lines of codes here. Now, due to this adaptability, bucket sort algorithm becomes slightly more complex, but is also the most versatile. Bucket sort is also known as bin sort algorithm. Is a sorting algorithm that divides the array's element into several buckets. The buckets are then sorted one at a time, either using a different sorting algorithm or by recursively applying the bucket sort algorithm. And this particular algorithm is commonly used with floating point values and when the input is distributed uniformly over a range of values. Here goes the algorithm. First we need to partition the given array into range into a fixed number of buckets. Then we need to toss every element into its appropriate bucket. After doing that, we need to sort each bucket individually by applying a sorting algorithm. And at last, we need to merge them or concatenate all the sorted buckets. Let us have a look at an example. See, the given series of elements are this: 12, 9, 24, 4, 19, 21, 14, 6, 2 and 16. So these are the elements here. So altogether we are having 10 elements, right? So we just placed their index as 0 to 9. Now we have taken here 5 buckets. Each of the bucket is having a capacity to hold 5 different values, right? So the capacity of a bucket is 0 to 5, right? And for every bucket can hold 5 different values. Now we will be putting these elements based on their number, based on the value, we'll be putting them into buckets. So 4 goes to the bucket 0 to 5, 2 also goes here. So 4 goes to bucket 0 to 5, 2 also goes in this bucket, 9 goes in the bucket having values 5 to 10, 6 also goes in this bucket. Then 12 goes to this bucket having value 10 to 15, 14 also goes in this bucket. Then 19 goes into the bucket holding values 15 to 20 and 16 also is included in this bucket. Then we are having values 24 and 21 which goes to bucket 20 to 25. Now that we have placed all the elements in their proper buckets, we can individually apply sorting algorithm for these buckets on their own, right? So here we will be sorting the elements within the bucket using any sorting algorithm. So here we can see from 0 to 5, 2 and 4 has been sorted. From 5 to 10, 6 and 9 have been sorted, and you can see here. Finally, when we take out the elements from the bucket, we will take out from this series, right, from the lowest value bucket till the highest value bucket. Okay, so this is the final sorted series that we are getting using bucket sort algorithm. We do have certain limitations of this algorithm. This algorithm may or may not be stable sorting algorithm, and it may not be useful if we have a large array because of the size of the array, it increases its cost of computation. It is not an in-place sorting algorithm because some extra space is required to sort the bucket. Here is the time complexity of bucket sort. In the best case and average case, it is O(n plus k), whereas in worst case, it goes to n square. That's it for today. Hope you have enjoyed this lecture. See you in the next lecture. Till then, take care.